L'Hopital's rule, it's not much notes to write on. It's kind of, you have to do example problems, I feel like. So that's what we're going to be doing here. So L'Hopital's example problem 1. So this is just going to be a handful of example problems because there's not much, it's not like a concept you can show just generically. You have to like use examples. So say we had the limit as theta approaches 0 of 1 minus cosine theta over 2 sine squared theta. What is the first thing that you should do every single time when you're finding the limits? If you remember from unit 1, what's direct substitution? Awesome. So what I want you to do is do direct substitution on this. Plug a 0 into this theta here and this theta here. What do you end up with? It is 0 over 0. It's 0 over 0. So a light bulb should be going off in your head. 0 over 0, that means I can use L'Hopital's rule. Okay? Before 0 over 0 meant, oh, you can cancel something out here. But rather than going through that hassle, it's a lot easier. Actually, this one might be kind of doable with that. We should do this both ways on this one. I didn't mean for that to happen, but anyway, 0 over 0, so we're going to do L'Hopital's rule. So what we're going to do, and this is the correct way to do it if you want full credit, you have to have limits in there. You have to have the LIM notation. What we're going to do is we're going to do the derivative of the top. So you're going to be left with sine theta. The derivative of 1 is 0. The derivative of cosine is negative sine, so it's negative negative sine, which is just going to be sine. Okay. The bottom derivative, you are going to have to use chain rule. So it's a layered function, so you bring the 2 down, multiply it in front, so you get 4 sine theta, and it's to the first power because you minus 1 from the power. But then you have to multiply by the inner derivative, which is cosine theta. If you notice, we're doing a lot of stuff from the previous unit. Okay, we're still going to do all those derivative rules. So if you hated chain rule and you hated implicit differentiation, they're not going away. Okay, it's going to be all over this unit. Okay, now if you notice, if you do direct substitution now, you would still get a 0 over 0. But you can obviously do a little bit of simplifying here. Okay, so this cancels here. 1 over 1. Now you plug 0 in. Now, as soon as you plug 0 in and you do direct substitution and it works, you don't end up with a 0 over 0, then you can get rid of the limit. Okay, because people are going to go, when do you get rid of the limit? When you do direct substitution. Okay, so right there, it'd be 1 over 4 cosine 0. Cosine of 0 is 1. You're left with your final answer to be 1/4. What I'm going to do now is, just because I think I can do this, I'm going to actually try to break this down using trig properties. But what's great about this is if you forget trig properties. You don't have to write this down if you don't want, because this might be a huge embarrassing failure. But maybe not, I don't know. All right, so this is going to be 2 times 1 minus cosine squared theta. Does everyone remember that trig property, kind of? And again, if you don't, it's fine. Doesn't really matter. All right. Well, 1 minus cosine squared theta. If you do difference of two squares there, you have 1 minus cosine theta and 1 plus cosine theta. Okay. Obviously, this is going to cancel here, so you get 1 over 1. Okay. And if you notice, you end up with 1 on the top because you can do direct substitution. Plug the 0 in at the bottom. It's 2 times 1 plus 1, which is 2. So you still get 1/4 either way. But you tell me which one's easier. And it's kind of up to you how you decide. If they do tell you you have to, absolutely have to use L'Hopital's rule, then you're going to have to use it. But if they don't, which a lot of times they don't say that, which most times they don't, then all you have to do is just do whatever you want. You can choose which way you want to do it. First thing you should do is what? Every time. Why is it doing that? Yeah, do direct substitution. Plug the 0 in. What do you end up getting if you plug 0 in there? All right, so that means don't wait for me. Do the derivative of the top, do the derivative of the bottom, and start solving it out. As you can see, algebraically, nothing would divide out on this one like we did the last one. So you're kind of stuck doing L'Hopital's rule on this. So the red step, I did the derivative of the top, the derivative of the bottom. then the orange step, I plugged in 0. So if you notice the LIM, that notation went away because I did direct substitution. And you end up with -1 over -2, which is just 1 over 2. Okay, plug in infinity, you'll notice you get infinity times e to the infinity over infinity to the 2 times infinity plus infinity squared. So clearly you get infinity over infinity on this one. So we need to do L'Hopital's rule. So let's take the derivative of the top and the derivative of the bottom. What rule do I need for the derivative of the numerator there? Product rule. Okay, so we got f prime g plus g prime f. Okay. Okay, and then we're going to do the derivative of e to the 2x. You need chain rule on that one. You end up with something like this. Okay. But the problem with this one is we still have infinity over infinity. That's embarrassing. No, it's not. It's by design, I promise. One way you can do it, I guess one way we could have done it from the very beginning was just get rid of this x squared. All right, we'll do that the next time through, because this is a L'Hopital's rule lesson. So that's gone. All right, so we're going to do the derivative of the top and the bottom again. When this happens, you do have to iterate L'Hopital's rule. So we have e to the x plus e to the x plus e to the x. This is what happens when you make up a problem. In the bottom, we're going to have 4e to the 2x plus 2. But since we are going to infinity, I'm going to actually get rid of that 2. If you wanted, you could do the L'Hopital's rule again, but I'm going to get rid of that. That's basically meaningless. And the top one, I'm going to divide by e to the x. And the bottom, I'm going to divide by e to the x as well. And you're going to be left with 1. You're going to be left with 2 plus x over 4e to the x. Okay. Again, that 2 is meaningless, but if you wanted to, let's just do the derivative of the top and the bottom again. You're going to get 1 over 4e to the x, which is 1 over infinity. And as Quinn said, it's going to be 0. This way took longer than the way that I taught you in Unit 1. Okay. In Unit 1, what you could have done, based on what we did in Unit 1, what you could have done is understood that the x squared is meaningless because we have a higher power on that e to the 2x. So what you could do is just get rid of that x squared right away. Okay, meaningless compared to everything else that's there. Okay. Then from here, use exponent properties, so we can divide this out here by this here to get e to the x. And you get 1 over e to the x. Well, 1 over e to the x is 1 over infinity. You end up getting 0 again. And so the quickest way is not always L'Hopital's. Sometimes it's faster to factor it out. Sometimes it's faster to do the rationalizing technique. If you had a rationalizing technique problem, to do the derivative of that might take a long time because you have the square root in there that you have to deal with, the chain rule. But I don't know. It's good practice there. Any questions on that? Cool. Great. Now I'm going to show you a weird one, just to kind of get you comfortable with seeing stuff that's kind of weird. For this one? All right, so, oh, whoops, okay. Well, the 2 is meaningless because we're going to infinity. I could have done the derivative again. I just didn't feel like having a long, drawn-out process. So I divide. So orange, I divided the top by e to the x. So that's 1, and then that's canceled. So that's 1 as well. So 1 plus 1 is 2, plus x is the 2x. Or I'm sorry, it's 2 plus x, I'm sorry. Does that make sense? And the bottom is, I divided this by e to the x. So what you can do, like say I did 4e to the 2x divided by e to the x, you can subtract exponents. So it's just going to be 4e to the x, because 2x minus x is x. Does that make sense? Yeah, I do skip over some of the algebra sometimes. I apologize for that, but if you ever do ask, just again, that's why I do the color coding. So. All right, this one's weird. It's meant to be. So we're going the limit as h approaches 0 of e to the h minus 1 over 2h? Yep, 2h. Okay, now just looking at this right now, what would you guess the answer would be? 0, infinity, some other number? Is it intuitive to look at that and go, oh, the answer is going to be kind of like this? Probably not. It's kind of weird. Yeah, you plug in 0, you get 0 over 0. So L'Hopital's rule does apply. So if you can, try doing L'Hopital's rule in your head. So what's the derivative of the top? What's the derivative of the bottom? What do you end up getting when you plug in 0? Does anybody have an answer just by doing it in their head? 0? Anybody else? 1/2? But you just wrote it down. Who said, was that a 1/2?
Yeah.
Someone said something.
Yeah.
Cool, thanks. I think that's the answer. It's always fun to like try to do it in your head and then see what the answer actually is. So if e to the h on top, the derivative of 1 is 0. We're also doing the derivative with respect to whatever's here. So that's another reason why I'm showing you this. If it's an x, then do the derivative with respect to x. If it's an h, you have to do the derivative with respect to h. The derivative here is 2. Okay, now you can do direct substitution. E to the 0 over 1, I'm sorry, over 2 is 1 over 2. Oh, it is 1/2. I know, I'm just kidding, dude. I respect you. So you get 1/2. What some students do is they see the h and they go, oh, I got to do the derivative somehow. That's the derivative definition. You can always, for the derivative definition, the f of x plus h, all that stuff, you can always do L'Hopital's rule, even though this is not a derivative definition problem. But if you ever see one of those and you don't know what to do, then just do L'Hopital's rule. It still works. Okay? Just to kind of show this point a little bit more, I'm going to use the exact problem that you had on the test to illustrate this. So the one on the test was, I believe, the limit as x approaches 2 of ln of x plus 3 minus ln of 5 all over x minus 2. If my memory is failing me on that one, it's fine because this is still a 0 over 0, so it still illustrates the point that we're trying to do here. Okay. So right away you can see, oh, it's 0 over 0, and then you might be thinking, oh, but it's the alternate definition, limit definition of derivative. How do I do that again? Oh man, I'm so confused. I don't know what to do. Well, then forget about all that stuff that you might have forgotten. Just use L'Hopital's rule. So we're going to do the derivative with respect to x on the top. You're going to end up with 1 over x plus 3 times 1, if you really want to be super technical, minus, what's the derivative of ln of 5? Nope. 0. It's a constant. Yep. Don't fall for it. Okay, the derivative of x minus 2 is going to be 1 minus 0, so I'm just going to put a 1 there. Okay, let's try to do some direct substitution since we're not dividing by 0 anymore. Do direct substitution. This is meaningless, meaningless, and meaningless. You do direct substitution, you end up with 1/5. Which, on the test, that was the answer. So if you don't like that alternate definition of derivative, then do L'Hopital's rule. You'll still be able to solve it. Okay. Okay, let's do the, let's go on to the next section. So this was L'Hopital's rule, just a brief snapshot. The only way that this can get a little bit harder is if EP tries to throw a curveball at you. I will throw a curveball at you tomorrow over this as a form of your warm-up. But the curveball is still not that complicated. This is a very straightforward concept compared to a lot of the other stuff in the unit. So that's 311. Using derivatives to find limits, values. Isn't it kind of weird to think about too? Like the way L'Hopital's rule works is you're using derivatives on limits, but limits are the backbone of derivatives. Remember the limit definition of derivatives? So it's kind of like meta in a way, but not really. But you know, does anyone think that's cool? I don't know, I like stuff like that.